I'm going to review the Module 6 topics in preparation for the test. So in Section 1, we talked about graphs of quadratic relations. So in our first problem, we're given a graph and we want to identify the vertex, the y-intercept, and the x-intercept. So the vertex is the highest or lowest point. We want to make sure we're paying attention to the scale. So my x value is going to be at 1 and my y value is going to be at 4. The y-intercept is where it crosses the y-axis. And again, we want to pay attention to the scale. Y-interceptors are always written as 0, a value, which in this case is 0, and 3. And lastly, the x-intercepts, where our graph crosses the x-axis. Okay. There are typically 2, and our two x-intercepts are at -1, 0, and at 3, 0. And x-intercepts are written with the number first and then 0 second. The second problem we're looking at says to determine which of the equations are quadratic. So quadratics are of the form y equals ax squared plus bx plus c. So that first term, y equals 3x squared plus 4x minus 10, is the exact form we talked about. So this one is a quadratic. Second one, we have y equals x squared minus 10. So even though it doesn't have that bx term, it has the squared term, which is the minimum requirement for a quadratic. So this is also a quadratic. Next, we have y equals 0.4x plus 5. So it doesn't have that x squared term, so this one is not a quadratic. And lastly, we have y equals 2 to the x minus 1. So in a quadratic, the variable must have a squared exponent, so that means x squared. This has 2 to the x, which is not the same thing. So that is not a quadratic. So next we want to talk about the three forms of a quadratic. So the first one is standard form. Okay. It's the traditional form, y equals ax squared plus bx plus c. Next we have intercept form, which is y equals a x minus p, x minus q. It'll tell us the x-intercepts. And lastly, we have vertex form, which is y equals a x minus h squared plus k. And it tells us the vertex. So each form tells us something different about a quadratic. They all have that a value in front, which tells us which direction the quadratic is going to open, but then they tell us different information after that. So our first thing we're going to do is determine the form of each quadratic equation. So we have y equals negative x minus 1 squared plus 5. So this is an example of vertex form. Y equals 2x squared plus 10x plus 5 is an example of standard form. Then our last one, y equals 4, x minus 2, 2x plus 1 is an example of intercept form. So just basically looking to see which form the equation is in. Tells us different information, like I said. So next we're going to write the vertex form of the graph below, and we're going to assume a equals 1. If a is ever not 1, I will let you know. So the first step is to identify the vertex, and I need to pay attention to the scale that we're given so that I can identify the vertex correctly. So the vertex is at -3, -1. So when we go to write vertex form, we start with y equals, and then our a value, which here we're assuming is 1. I also want to make sure I look to see which direction the graph is opening, and this time it's opening up, so we also have a positive. So we can start directly with the parentheses. So when we write vertex form, it's always x minus h, and h is the x value from the vertex. But we'd be subtracting -3, so it's going to be the opposite of h, so x plus 3 squared. And then we keep the sign of k, which is -1. And I highly recommend that after you've written an equation in vertex form, you graph it in Desmos to make sure it matches the graph you're given. Or if you're given the vertex and you're putting it in vertex form, you graph it in Desmos and that the vertex matches. So definitely use Desmos as a way to check your work here. So section 3, we talked about converting between the forms of quadratics. So if we're given the quadratic y equals 3x minus 5, x plus 8, we want to write it in standard form. So that means we have to distribute. We have to use FOIL. So first I'm going to do 3x times x, which is 3x squared. Then 3x times 8, which is 24x. -5 times x, which is -5x. And then -5 times 8, which is -40. Lastly, we're going to combine like terms, and you get y equals 3x squared plus 19x minus 40. If you don't have an x squared term, it is not a quadratic. So remember that. Okay. Next, we want to convert the equation in standard form to vertex form. So y equals x squared plus 4x minus 7. So the first step is to actually figure out where the vertex is. And we can do that using Desmos. So I graph the equation in Desmos. I identify the vertex, which is at -2, -11. And then I'm going to put it in vertex form just like we did on the example above. So y equals, if there is a value in front of x squared, such as 2 or 3, it's going to be my a value. A stays the same between the different forms. So there's nothing there, so we're going to go ahead and leave it as 1. And then we do the opposite of what's the x value, so x plus 2 squared, and then we keep k minus 11. Lastly, we're going from standard form to intercept form. So y equals x squared minus 7x plus 12. So we have two options here. You can graph it in Desmos and find the x-intercepts, or we can factor. We're looking for the numbers that multiply to 12, but add to -7. So if you think about the ways to multiply to 12, you got 1 and 12, 2 and 6, and 3 and 4. And the only way to multiply to a positive and add to a negative is if they are both negative. So -1 and -12 won't work, -2 and -6 won't work, but -3 and -4 will work. So we have x minus 3, x minus 4. If we were to go the other route, where we use Desmos to find the x-intercepts. So the x-intercepts are at 3, 0, and 4, 0. So if you're given the x-intercepts and you're writing it in intercept form, you do the opposite of each in parentheses with x. So that's why it's x minus 3 and x minus 4. And a. So section 4, we talked about transformations. So contraction, expansion, vertical shift, horizontal shift, and reflection. So in the first one, we're going to list the transformations from our original graph, which is the dotted one, to our transformed graph, which is the solid one. So first thing I notice is that it is a quadratic and it's opening a different direction. So I know that there is a reflection. Okay. I also, if we're looking at quadratics, we pay attention to the vertex. I also notice that we have moved left. So moving left and right, that is a horizontal shift. So there is also a horizontal shift. So next, we have a graph, and we haven't really talked about its equation, so we don't know what we're basing it off of. But we do have this y-intercept that we're going to use as our kind of point to figure out what we've done. So I do notice that the graph has moved up. So we do have a vertical shift. Okay. If I also look, the graph isn't the same width as the first graph. It looks to be farther away from the y-axis, which means we also have an expansion. So if your graph gets farther away from the y-axis, closer to the x-axis, that's usually an indication of an expansion. If it gets closer to the y-axis, that's usually an indication of a contraction. So next we are given an equation called the parent graph, and we want to list the transformations of the new graph. So we have y equals the absolute value of x as our parent graph, and our transformed graph is y equals -3 absolute value x plus 1. And you can use Desmos to help you identify the transformations if you can't do it solely based off the equation. So one thing I notice is in front of the absolute value, we have a value greater than 1. So a negative in front means there is a reflection. A value greater than 1, ignoring its sign, indicates there is also a contraction. Remember, numbers greater than 1, ignoring the sign, mean a contraction. Between 0 and 1 is an expansion. And if you look at the graph on Desmos, it has gotten skinnier. Lastly, we have inside the absolute value, we have that plus 1. So something happening inside the function with x means there is a horizontal shift. We've actually moved left. So horizontal shift. Okay. The last one we're given is the parent graph of the quadratic, y equals x squared. And we have our new graph, y equals x minus 2 squared plus 10. So we always use vertex form to identify transformations. So inside the function, we have the x minus 2. So inside the function means moving left or right. So we have a horizontal shift. Specifically, we moved right 2. And then lastly, we have that plus 10. So outside the function with the adding and subtracting, that moves up or down. So that is a vertical shift, more specifically, up 10. So in section 5, we talked about the quadratic formula and used it to solve quadratic equations. So x equals -b plus or minus the square root of b squared minus 4ac all over 2a. And it's extremely important before you use the quadratic formula to solve that your equation is in standard form, which means it's equal to 0. So our first example, we have x squared minus 12x equals 28. So it is not equal to 0. So that's going to be my first step, actually, to subtract 28 from both sides. So we have x squared minus 12x minus 28 equals 0. So next I'm going to identify a, b, and c. So a is the number in front of x squared, which in this case is 1. B is the number in front of x, which is -12. And c is our constant, which is -28. So plugging it in, we have x equals -b, so -12. Plus or minus, under the square root, -12 squared minus 4 times 1 times -28 all over 2 times 1. So now I'm just working on simplifying the equation. So -12 turns into a +12, plus or minus, under the square root, -12 squared is +144. -4 times 1 times -28 is +112. all over 2. Next, we're going to add 144 and 112, and we get 256. Next, we want to either simplify or take the square root of 256. And in this case, the square root of 256 is 16. So we have 12 plus or minus 16 all over 2. If we get a perfect square, what we want to do is actually find our two solutions. So our first solution is 12 plus 16 all over 2. 12 plus 16 is 28. 28 divided by 2 is going to give us 14. Next, we're doing 12 minus 16 all over 2, which is negative 4. And negative 4 divided by 2 is negative 2. Next example, 2x squared minus 14x minus 13. It is equal to 0, so we can identify A, B, and C. A is 2, B is negative 14, and C is negative 13. So we're going to plug it into the quadratic formula, and we're going to get negative 14 plus or minus the square root of negative 14 squared minus 4 times 2 times negative 13 all over 2 times 2. We get 14 plus or minus the square root, and then negative 14 squared is positive 196. Negative 4 times 2 times negative 13 is positive 104 all over 4. So we get 14 plus or minus, and then 196 plus 104 is 300 all over 4. Now 300 is not a perfect square. So what we want to do is we want to break it down. We do not want to write the decimal. So if I break down 300, I can break it down as 100 times 3. 100 is 10 and 10. And those break down as 5 and 2 and 5 and 2. So if I look, I have a pair of 5s and a pair of 2s. So when we simplify it, we're going to get 14 plus or minus. If you have multiple pairs of numbers, they multiply together. So we'll have 10. Underneath the square root, we had the 3 all over 4. My last step is to simplify the 14, the 10, and the 4, and they're all divisible by 2. So we're going to get 7 plus or minus 5 square root 3 all over 2. Lastly, in section 6, we talked about solving nonlinear systems, which we use Desmos for. So what we do is we graph both equations in Desmos and find where they intersect. So y equals negative x plus 4, and y equals x squared plus 4x minus 2. So you may have to zoom out to see the entirety of where the two graphs intersect, which in this case are the points negative 6, 10, and 1, 3. Our second example, y equals negative 2x squared plus 2, and x squared plus y squared equals 4, which is a circle if you graph it in Desmos. And it actually is going to have, in this case, 3 intersection points. So the first one is 0, 2. Then we have negative 1.323, negative 1.5, and then 1.323, comma, negative 1.5. So you can have, depending on what your two equations are, 2 solutions, 3 solutions, possibly 4 solutions. It really depends on what the equations are. If you have any questions, please don't hesitate to reach out.